being late. Me too. Like, holy God, you weren't late. Philadelphia was late. What do you call it? Welcome to the 2024 Bill Berner Physics Demonstration Show. I am Mary Markapole, the Lecture Demonstration Coordinator here. I have an important question for your teachers. If we ran like 10 minutes over, are your buses gonna like freak out? Or would you survive?
They're going to be late getting here anyway.
Good call. Good call.
So that's fine. Yeah.
All right, cool. The next person I'm going to introduce, I'm going to go in a different order from yesterday, is my work brother, Mr. Peter Harnish, and he will run us through the other.
Hi, my name is Peter Harnish. I am the undergraduate lab manager here at the physics department. That means that I design, run, teach people how to teach the 100 and 200 level physics labs for anyone taking physics here at Penn. This is kind of not my normal gig. I'm usually the numbers hard science one of us, but it's fun to do this for people who legitimately just always want to be here. The third part of our trio.
I'm Ryan Becky. My title here is Active Learning Coordinator. What that means, I help the professors in the physics department do anything beyond lecturing, which is pretty important, I think. Before that, I spent many years teaching high school physics in Philadelphia. And Mary already talks. Bill, this is the namesake of our show.
Woo!
And I am the fourth member of this trio. I did this job for 20 years waiting for somebody to come along who could take my place, and Mary finally did, so I retired. We started this thing a while back. It is gratifying that these guys think it's worth continuing, and I don't know why my name needs to be everywhere, but it's very cool regardless of what we do to keep it going. Thank you for coming. I taught high school for 25 years, and then I came here for 20 years and worked with people in college. In high school, I had students and no equipment. Here, I had equipment and no students. And we put this program together because I figured high school students needed to see this stuff. And that's the plan here. You're here because Penn has resources that your school just can't bring to bear. So you want to, pay attention to this. If you don't need it right now, you may need it later when people get to those things. Remember what you saw. But the other reason for coming here is that you're in an arena not only where science is taught, but where science is done. And so you came in through the intersection of 33rd and Walnut. I don't know quite how long it took you to get here. This is one of the most interesting intersections in the city. Here's Walnut Street running east-west. Center City's down here, West Philly's out there. Here's 33rd, North Philly's up here, South Philly's down there. We are at this corner, okay? In the mid to late 1940s, okay, two really important things happened. I was born, and Penn developed the ENIAC in this building. So right across the street, when you walk out those glass doors, the building across the street is a big red brick, looks like a factory because that's what it was in the beginning. Penn bought it, converted it to the electrical engineering school, and in the 40s, Mauchly and Eckert filled the basement with vacuum tubes and built the first digital computer in the world. It was right there. It started right at that corner. If we go catty corner across, we've got the Laboratory for Research into the Structure of Matter. A very interesting building built in the early 70s because at that point in time they realized that chemistry had done most of what you could do with chemistry, physics had done most of what you could do with physics, but that boundary line between them had lots and lots of things to be done. And if they put up a building that they didn't call either, both groups could work together. It worked marvelously well and continues to work that way. They're doing something called condensed matter physics over there. But where am I? 1975, they developed electrically conductive plastics, which it took 25 years to appreciate, and they were awarded a Nobel Prize for it in 2000, okay, in that corner building. If we come down to our building here, this has been here for quite a while. Lots of interesting stuff has happened. They built the detectors that detected the Higgs boson just back in 2012, okay, but in the 60s, Ray Davis concocted a device that would detect neutrinos from the sun, but it only detected a third as many as he expected. In the 60s, people said, well, you know, this is a pretty shaky experiment, we probably screwed up. It took until 2002 to realize that Ray had done it right, the astronomers had done it right, but the people who did it wrong were the particle physicists who didn't understand neutrinos. And so that was a very big discovery, and Ray was awarded the Nobel Prize in 2002. More recently, Jean Malie and Charlie Kane developed topological insulators, which are materials that only conduct electricity on the outside atoms. And this gives you really wonderful electrical properties. All sorts of things can happen for that. That won the Breakthrough Prize, which is 3 times as big as the Nobel Prize. This is a very promising development. So they're writing the science books here as well. And you're in this building, okay? So kind of soak up a little of that atmosphere, all right? Like, they're not just using the books, they're changing them. So this is a great place to be. I'm glad you're here. Take advantage of everything you've got, and you know, don't forget any of it, because it's going to come back and you'll use it at a later date. Thanks.
Thank you, Bill.
We're going to talk about the last corner.
Oh, yeah.
This is actually, Pete made this point a few years ago. This is actually the most important building on that corner. No research happens there. It's a dormitory. This university can't do what it does without students like you, right? This could be you joining in, setting a path to become a graduate student or a postdoc or do research and be working right here in this building, writing the lines in the physics textbooks. You know, so pretty cool stuff. And without further ado, I'm going to hand it over to Ryan, who's going to start talking about Newton's laws.
Thank you for coming. We're so glad you're all here. You're just in time to hear the physics. So, the scientist's stock in trade is a claim backed by evidence. And the story gets started a few centuries ago when sort of physicists came into being and sort of claimed that territory and took it from the philosophers. And one of the first interesting questions people who cared about direct observation asked is, how do things move? Why do they change how they're moving? What do things do? What is motion? I'm not asking you to think this is the best question in the world right now. I'm just sort of trying to direct you towards what everybody cared about at the time. And it was an actually controversial question. How do things move? So we're going to take some mass. And I'm looking around for a particular piece of mass.
You want to stand on it?
What's that?
You want to stand on it? I'll go gently.
Yeah. I can volunteer to be the mass. And I'm on a cart. And Pete is going to give me a little pull. I was at rest, and now I'm not at rest. Why am I not at rest? Dumb question. I thought you guys were smart here at Penn. Pete pulled on me, right? So let's try something else. So now Mary's going to get up.
Step down.
Yes. Take your time.
Nice save. Okay.
And Pete's going to try this again. We have mass at rest, and Pete's going to give it a tug. So, yeah, it's fine. Yeah. Every time Mary demonstrates her skills on wheels, it's worth an applause. All right, let's see it again. Mass at rest, and it gets a tug from the rope. Ah. So the statement we want to make, we want to complete the sentence. Objects at rest tend to stay at rest. So why was I moving, but Mary wasn't? Friction. My feet were stuck to the platform. And also, maybe you heard me tell Pete, please do it gentle. If he had gone really fast, I think my feet would have gone with the platform, but my head wouldn't have. Then we got a rotation. And I don't have a helmet on. So let's think about this a little clearly. If I apply a force to a piece of mass, I can get it to move around. This is like me standing on a slow-moving platform. But if I apply my force really quick to one of those masses, this one didn't go there, right? Maybe. I'm applying a force to this stack of blocks, and only one of them is doing something. Objects at rest, which this bottom block was, tend to stay at rest, unless acted on by a force, an outside force. So I can, push all of them, and all of them go. What's surprising in this demo is the top ones don't go. They didn't get hit by the hammer. This feels weird, like this is an obvious statement, right? But that's only half the story. Then it would dictate that objects in motion tend to stay in motion, if you keep pushing them. I'll say that again. I'm like planting an Aristotelian false sentence. I'm putting it out there. By this logic, it could still be that objects in motion are only moving because you're pushing on them. Like, I haven't pushed like a wooden stone cart on a gravel path lately, but I've got the next best thing. I've got this cart with really bad bearings and wheels, and it's kind of frictiony, and this object is in motion, but if I stop pushing it, it stops. We can do better. We forgive the ancients for having this idea because they didn't have Mary's roller skates. It's a technological thing. Galileo was able to do experiments that revealed the law of inertia. It's the first time I'm saying that word, I'm aware of it. Resistance to change. Mary's at rest once again. She's not on the platform this time. This time, the hammer, quote unquote, me, is going to push on this mass, and it's going to go and go and go and go. It wasn't like the cart, right? It wasn't like the ox cart in ancient times that didn't have to have brakes because it just stopped when you stopped pushing it. When I push this mass, it goes and goes and goes and goes and goes until acted on by an outside force. So we can do this every which way over and over and over again. We can make the bearings better, or we can put hockey pucks on ice. And the conclusion we get to now, because we're able to do a different experiment, is that objects in motion tend to stay in motion unless acted on by a force. So this is interesting. We've got a law of inertia. Things resist change. Things are going to maintain their state of motion unless you do something to them. And once you have a new general principle like that, which is really the heart and soul of like what you're trying to do in a physics department, you're able to do a different kind of experiment and think about things totally differently. So everybody had pendulums in the ancient world, and you kept time with them, and that's all fine and good. We knew that the period was repeatable and it was the same every time. But after you have a law of inertia, this law that says things tend to maintain their state of motion, which applies also to moving things, then you think about the pendulum totally different. And you say, well, there's been this idea around that the Earth is the thing rotating, not the heavens and stars rotating around a fixed planet, but instead the Earth is spinning and it's the stars that remain fixed, right? This was a controversial idea. Sadly for some it still is. But so a French physicist proposed that if you put a pendulum at the North Pole up on top of the spinning thing, you won't see. Let me just show you what you see. Is that camera working okay? All right, so let me orient you to what I got going on here. I have a pendulum, and it's at the North Pole, and we've got a camera way up on the ceiling looking down on the whole thing. So the other thing the ancients didn't have the luxury of was getting out into space. You couldn't observe the Earth from outside. You couldn't make a direct observation of the Earth spinning, right? So the other camera we have is attached to this contraption, and when I rotate this, you see how my arm's moving, but nothing, the map's not moving? You're all out there seeing the map move because it's on my table taped down. So I'm able to do this experiment where I can get a pendulum going on the Earth, and the law of inertia now says it's going to maintain a straight line swing. It's a new idea. Is it maintaining its straight line swing? Man, biggest audience yet and the fewest volunteers to say something. Is it going in a straight line? Sorry, who's saying yes? Why do you think yes? Yeah, right back here. Yeah, do you want to say why you think that? Yeah.
Yeah, exactly.
Stop. Yes. You're able to be out there. Yeah, you don't have to overthink it. I'm standing here, it's going in a straight line. If you wanted to say no to that, I appreciate you're going out on a limb. You're looking at this one. You are an average person in the 1770s who sees this erratic swinging and thinks, my pendulum's wonky. Why would it do such a thing? The trick of this demo is that we are able to allow this to pivot so that this inertia that this pendulum has, it doesn't have to obey. It's not like a rigid fixed piece of metal that's swinging in a hinge, right? It's not a door. It's a string that can twist. So if you rotate your planet around that apparatus, law of inertia dictates it keeps its straight line. But we see craziness if we're stuck on the Earth observing how the pendulum acts. Now, we just had a special visitor to our house, and I shamefully skipped over one of the coolest parts of this demo. Here's your observer at the North Pole. It's just a stuff. It's not conscious, don't worry.
I'm gonna do this for elementary school. The kids
So
are
can we
like,
get-
"Stop."
Well, okay, we can have that talk. So, if you have any opportunity, this is the Foucault pendulum at the Franklin Institute. If you have a chance to go there, make sure you visit this. It's in a stairwell. Visit it when you first arrive. Because what they do every morning is they pull this 3/4 ton mass on a steel cable back 4 or 5 feet radius away from the center, and they let it start swinging. And it has one of these attachments at the top that's allowed to rotate freely, so that as the Earth spins around it, as the building, the Franklin Institute spins around it, it doesn't spin. But it appears to spin because of the law of inertia. And what they do is you can know what time of day it is based on how many of these pawns it has knocked over. Because it'll just go through its march in time minute by minute and knock one down every few minutes. Yeah.
We are going to directly address that in a couple things about how we can move with an object or not with an object, and be able to tell if we are moving with it or if it's moving independently. We are going to get to this.
Thank you. It's about the attachment. If you're walking around on the earth, you have no choice but to keep your frame of reference is moving with you. Like you're only moving in relation to like 33rd Street, Walnut Street, the aisle. But if you could separate from the earth and not be coupled to it, attached, it could do its thing independent of you. And if you stay still, it can move around under you. See what I'm saying? If you still have this question in an hour and a half, let us know. Thank you for asking.
Yep. What? On me?
Yep.
All right. Cool. Yeah, get it right. All right, so we are now firmly in the realm of doing some science, and as kind of the hardest science of the group, it falls to me to talk about this, that when we are doing science, we have to be very specific in our language, right? When I, as a scientist, say a hypothesis or a theory, I might mean something very different than someone who is writing a book for an airport about a theory or a hypothesis, right? So we have to be very specific in our language. What we've just talked about is the law of inertia. What are the units of inertia? Does anyone know? When we're doing science and we're trying to measure inertia, what are the units? Newtons is a guess. So, what is the other word for inertia that you may have heard of? Right? We say inertia. The other word that might get thrown out is mass. Right? So inertia is a property. When we describe it as something has inertia, the units of measuring inertia are its mass. And if we need to put numbers on that, what are the units on those numbers? Kilograms, right? So inertia has units of kilograms, right? That is the SI standard. That is, what they use everywhere else. If we were to transfer that into the American system of measurements, gallons and whatnot, what would be the unit of mass? What is the unit of inertia in the imperial unit system? That's right, slugs. It's in slugs. Right, so, I heard pounds, right? We generally talk about pounds, right? So I imagine a lot of you occasionally, due to social pressures, look at a thing that is measuring the pounds that you have, and you feel bad about it for terrible patriarchal reasons probably, right? So we're measuring, your weight is measured in pounds. If we go into SI units, right, we go to France, and we're trying to measure your weight, what are the units that would be on the scale in France? Newtons. Your weight is in pounds or newtons. Your mass is in kilograms or slugs. Now, I know a lot of you have never heard of the unit slugs because we don't use it. Because in America, historically, we are very sloppy with a lot of our bookkeeping. But we can be forgiven for confusing mass and inertia. Because this is admittedly slightly a guess, but I feel like I'm not stretching here. None of you have been anywhere that isn't on Earth, right? And on Earth, gravity is effectively constant. Right? So gravity is about the same everywhere on Earth. Your mass, your inertia, is how much of you there is. Your weight is how hard the Earth is pulling on you. And just about anywhere on the planet, those numbers are at a fixed proportion. Gravity is about the same everywhere. But that is not absolutely true. Very technically, if you were to go to the top of Mount Everest or down by the Dead Sea, your weight would be different because there's a different amount of gravity pulling on you. Right? So let's take this a step further, right? Let's imagine that we're not here in Philadelphia, right? We're hundreds of years in the future, and this whole classroom is in space, right? So we're now on a space station. We're still in class because it's Philly, and you still show up to class, right? So let's imagine that this classroom is up in a space station, right? And we're normal, we're doing our things, we're having our classes, and that's fine. But then, there's some weird space wind, something or other, right? And it knocks out a bunch of power, and we all have to deal with that, right? So, whatever breaks because of the space wind, and the artificial gravity is gone. You still have to show up to class, because that's how you do. But we're now sitting in class in a weightless environment. There is no gravity, right? We're all kind of just floating in our seats, and we're weightless. I'm up here lecturing, and let's say, just purely hypothetically, I notice you're on your phone and half asleep, even though your teachers did so much work to get you a field trip to come here, you're half asleep and on your phone. And I've had enough of this, and I take a physics textbook and I throw it at your face. We're weightless. We're in space. This book has no weight. How concerned are you about being hit in the face by this book? Right, you're not concerned at all. So, we've already established here, an object in motion will stay in motion, right? Unless a force acts upon it. So I beam this book at you. It is now in motion. What force is going to stop its motion? That's right, the gentle cartilage of your nose, right? That's what's going to stop this. Sure, if I let go of this book in space, it'll still float here, right? But if I get it moving with some motion, some speed, it's still going to take force for it to stop. And that force is going to be supplied by your face, right? So it's still going to take force to stop this. Yes, question?
So even if it, let's say if it did hit the force from the
Well, it's still going to, that depends on how squishy your face is, really. But the point is that there's this much mass moving, and the only thing that would stop it is your face, if I'm throwing this at you. We can even bring this a little bit closer to home. I imagine a lot of you have been in a weightless environment at, say, Hershey Park or Dorney Park or something like that, right? Then you're on one of these rides where they lift you up terrifyingly high and drop you in some form. You're on a roller coaster, you're on the elevator drop, whatever. You are falling. In that moment, you are weightless. In that weightless moment, if you get hit in the face with something, is it still going to hurt?
Yeah.
You're weightless. It's weightless because it's flying at you while you're dropping, and you're still going to hit in the face and it's still going to hurt. Right? It is the mass of the object that demands the force, not its weight. Right? So, with that in mind, and that specificity, and because I am the data one, it's time for quiz. Yeah, field trip, still have a quiz, deal with it. So this is a 3-kilogram mass, which for the gallon people is like 7-ish pounds, right? So this is about 7 pounds, and it is hanging on this string that would break with 10 pounds. So this string is just strong enough that if I was hanging 10 pounds on it, it would break. But I'm only hanging 7 pounds on it, so it is fine. I have more of this string, that I'm going to put here. This is again that same 10-pound string. Right? And the question is, if I pull on this string, which of these would break first? So there is this safety cord here, right? Which is just there for, I need to do this show a couple times reasons, and I don't want things to break. But notice, it is slack. It is not holding up any weight, right? So there's only this string and this identical string down here. If I pull on this bottom string, which of those will break first? All right, I hear a top one. Why top one?
Because you're putting more attention on it.
All right, so we have a guess up here that the top one will break first because it has all of this mass hanging on it plus how much I'm pulling. While this bottom string just has how much I'm pulling. All right. Any other thoughts? Everyone is going to fall in line behind your apparently appointed leader. And we're all thinking that this top string is going to be the one that breaks first. All right. Hopefully your faith is well put. All right, so the bottom string broke. What did we say a mass at rest tends to do? A mass at rest tends to stay at rest, right? For in the danger of personifying things, this wants to stay still, and I am pulling on it. It wants to stay still, which means that these are going to stay the same distance apart from each other. And my string is really only pulling on this. Does that make sense? We understand how this inertia is acting like a buffer, right? This is the reason why it's like safer to be in a giant SUV in a car accident than on a bike, right? Because you have all this mass that doesn't want to move and is protecting you. So as long as you have a big mass here, right, you can kind of worry easy, right? You don't have to worry about things. It's not going to be a big problem. Oh no, he's a huckster. Oh no. Why did the top string break?
Is it because you put the force on slower?
All right, so the top string broke for the reason you originally said. I was pulling on it, and I had additional weight to pull. What was different about that pull? It was slower. Why would slow matter? Why would it matter? Yes? Perfect. That is exactly what I was hoping someone would say. Right? You've already seen this demo twice. When we do something fast, pulling something out from under Mary, hitting something with a hammer, things that are still want to still, and only the thing that you're pulling on will be affected. When we do something slow, right? When we're pulling all 3 blocks slowly, when we're moving it slowly, then it has time to move and it can hold together. We can show this by slowing down this whole event by using a bungee cord instead. So I'm going to put a bungee cord on here, right? We can see right, it is bouncing on that bungee cord. And if I pull this slowly, I can get it to bounce. Right? I'm going slow enough that this tension never gets passed. I can move this around and that can then move. But watch that distance. If I go quickly, I can break the string before this has a chance to move. And then that inertia is protecting what's above it. So that was your first quiz of this. I'm not going to promise there aren't going to be more quizzes, so you might want to keep paying attention. See it? Phone, sleeping. But I'm now going to pass this off to Mary, who's going to bring you into the next one.
I'm here to talk to you about a couple of things that your teachers are talking about ad nauseum. I want to point out our sense of having weight comes from us pushing on stuff. So when we say we're weightless in space, it's not that you don't have weight, may actually be less because you're in a lower gravity environment, but you feel weightless because you are not pushing against the object that would normally provide you with resistance, or normal force, you may have heard your teacher say. But I'm going to talk to you a ton about Newton's second law. And by a ton, I mean like less than 5 minutes, because your teachers have talked to you about it a ton. What's Newton's second law? Actually, somebody knows. It starts with an S. It's not 4 letters.
Yeah.
What? Where?
Yep.
Force equals? Mass times acceleration. Isn't it cool when they're like, understand the universe through math? Isn't that great? It's just so lovely. I understand everything now because math. No, it's terrible. But the wordy version is worse. The acceleration of an object is directly proportional to the net force acting on an object and inversely proportional to its mass. That is just F equals ma in words. And now I don't have any breath left, right? So we're going to talk about what that means. Acceleration is directly proportional to net force. What is acceleration? Right, the rate of change in velocity with respect to time. I'm so sorry, teachers, because I'm going to take exactly your definitions and just crap on them. I'm sorry. Those definitions are completely accurate, but in your heart, you don't really feel like that. I know what that means. There are 3 ways to accelerate your car. What are they? An accelerator, that is completely not descriptive because there are 3 accelerators in your car. How do you get faster in your car? Gas pedal, right? Getting faster, changing your velocity, that's acceleration. How do you slow down your car? The brakes, right? Decelerating, slowing down your velocity, decreasing your velocity, that is, well, decreasing your speed. That is an acceleration. What's the other one? Steering wheel. If you change your direction, you've changed your velocity. All of these are changes in motion. Newton's first law, stuff stays where you left it, right? Why do we have where's the remote up there before? Because your parents know this without a physics degree. Mom, where's the remote?
Wherever you left the remote.
Right? That's Newton's first law, Captain Obvious. Second law is essentially nothing changes unless you force it to. Does that make sense? So if I take this chair, its motion is at rest, and I give it a push. Look, I forced it to change. It accelerated. That's very exciting. Directly proportional to net force, if I push harder, will it change faster or slower? It'll change faster. Wow, please protect the camera. Thanks so much. All right, so that's the first part. If you push something really hard, it'll get really fast, or it'll get slow really fast. That's the first part. The second part of Newton's second law, acceleration is inversely proportional to its mass. What does it mean to be an inverse? As one gets big, what does the other one do? Gets small, right? How can I change the mass of this chair? Check out my lovely friend, who is relatively massive compared to the chair, right? Right? So, I'm going to take this chair now, I'm going to push it the same way, and I got pushed back. That's a separate lesson. But, did Pete accelerate in the chair? No, not very much. It's a very tiny acceleration. What if I push harder? If I push more, we'll have more change. But still not as much change as before, because now we have more mass. So if you push something really hard, it'll get really fast. But if it's massive, not so fast. Right? Don't you feel like in your heart you knew that before you knew F equals ma? Right? And so that's Newton's second law in kind of like a, think of it a little faster before you go diving into your problem. I don't know if I can set Pete up. Oh, right. And we talk about it because I feel like it's my responsibility to talk about it. But also because I don't think we ever talk about it in those Captain Obvious kind of terms. Right? We get into the nitty-gritty of all those math problems. So now, if it takes a force to make a change, then let's take a look at an object that has a steady force acting on it. It could have happened.
Bummer.
Ready?
Sorry. Try to show off.
Yeah.
What did we see there? Did it stay in a constant motion? It looked like it changed to me. Constant motion is a straight line with a steady velocity the whole time, right? Right? That thing, it slowed down, it sped up, it went up, it came down. It was an emotional roller coaster. Maybe not that last part. right? So what's happening there? We have a single steady force acting on that object once it leaves the launcher. What's that single steady force? Gravity. Which way does gravity pull? Down. All right, awesome. How come it was able to move forward then? Right, there was some kind of force applied to it inside the launcher. But once it leaves the launcher, it's just heading across the room in a straight line, right? Like just like this ball is staying steadily with me the whole time, right? But gravity does something different. Gravity slows it down on the way up, speeds it up on the way down, right? As long as I throw it straight up and down. Is that reasonable to everybody? So what happens when we put them both together? Right? It stays with me. I'm launching it straight up, and it's, that time I launched it a little bit back. Hold on. I'm launching it straight up, and it is traveling with me. Is that reasonable to everybody? Gravity acts in the y direction, and there's nothing pushing this ball forward or back in the x direction. You can go ahead. Thank you. Gravity is powerless to affect forward and back motion. Right? We like to say in physics class that x's and y's are independent of one another. Don't mix your x's and y's. Mix whatever you want in your social life. I mean, not drugs, but I mean people. You know, love who you love and all that stuff. But don't mix x's and y's, because when you do it, your physics teachers look at your work when you're like, oh, this is the range. Now I'll put it in y equals 1/2 at squared. Your parents are, or not your parents probably like, well, I don't know what happened here. But your teachers are like, wow, we covered it like 18,000 times. So, and I figured out what the issue was with this. Because otherwise it's sitting on instead. All right, so what do I have here? I have a ball launcher, and because, you know, as you do, and it has a spring-loaded dowel on it. I'm going to put a ball on one end, and when I release the spring, the dowel will move and release the ball straight down. What will bring the ball down to the ground? Gravity. And then I have another one over here. When I release the dowel, it'll smack that ball. What will bring the ball down to the ground? Gravity. But it'll also fly forward, right? So I'm going to ask you a question, not the question that your teachers ask you. When they get to the ground, which one will be faster? See, somebody did that to me yesterday. They just pointed, but I couldn't tell which one they were pointing to, so they just kept pointing. Right? But I feel like you were leaning towards this side. Right? The one that's launched will be faster when it hits the ground because it's moving forward and it's moving down, right? And blah, 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 triangles, we can get a faster velocity out of that. All right. So if this one's faster, which one gets to the ground first? Well, I'm giving a quiz too. Hey. Same time. Why? You just said this one's faster. Right. Yeah, gravity's independent. They're going down to the ground at the same rate. So let's see if this is true. I have metal plates on the floor so we can hear this happen. Are you ready? Right? You then heard the other one bounce. And this one just rolled away from me. Where'd it go? Where did it go?
Left, a little left.
To the left.
To the left?
Toward the audience.
Toward the audience.
Under the flag.
Oh, I see it. Thank you. All right. So that one was really convincing, so I feel like I don't want to do it again because it was already perfect. Right? But so what's happening there, if I looked at this from this angle, I would see these two objects looked basically identical to one another. They would be falling at the same rate, right? Gravity acts in the y direction. It has zero impact on the x direction. And this is like the most important thing that your teachers want you to know in the first month of the school year. Is don't mix x's and y's. They are like Capulets and Montagues, and people die when you mix them. Okay? So I'm going to pass it off to Ryan, who is going to elaborate on this concept.
Yeah, at the risk of repeating what Mary says, x's and y's don't mix because now we can add another kind of clause to Newton's laws. Things in motion tend to stay in motion unless acted on by a force, and then they will change their motion in the direction of that force. So, something we didn't really have the luxury of doing until we had film motion pictures is to track the motion of a quickly moving thing in time. When Mary was tossing the tennis ball, the discerning eye will notice it's making little arcs. If you're just thinking about the ball and Mary, it's like you're on the Market Frankfurt line. You can juggle when you're on that thing, when you're between stations. But when it's pulling into a station and stopping, all bets are off. Because if the ball's up in the air, this is part of your question earlier. If the ball's up in the air and the train and you stop, decelerate, that thing's up in the air and it's only feeling gravity. So it will land somewhere else. So we've built this really cool contraption that shows you the trajectory of a launched piece of mass. This thing was shot in one direction. And the law of inertia dictates if there's no forces, it's just going to go as the metal rail goes. It'll keep traveling along this line in perpetuity. We all live on Earth, we know that doesn't happen. It does what these pink balls have shown us it is doing. It's showing you a picture of gravity independent of horizontal motion. What we've done here to get that point across is we've put our strings that these pink balls are hanging from equally spaced along the rail. So if like this is 3 inches, then this is 3 inches, and this is 3 inches, and this is 3 inches. That doesn't mean a lot to you until I say that each of these, let's imagine they're photographs taken every 30th of a second. You're filming this thing, right? So it takes a picture now it's the second picture, another 30th of a second, another 30th of a second, and on and on. You develop all these photographs and you put them in sequence and you say, oh, if I only trace back up to the rail and I measure sideways where this thing is, it's only achieving equal distances in time. And if you know anything about velocity, if you know the thing you need to know about velocity, you know that means that if these are equal pieces of time and these are equal spaces of distance, that is a constant velocity. So if you had done this out in the middle of space, it would have just kept, we would have only had to have this length of string to show you a straight line motion. But we're showing you the effect of gravity. The other thing that we've done is make the strings a little longer each time to demonstrate like the nature of gravity, right? What does gravity do to stuff? It accelerates it in the direction of gravity. So while it's not accelerating this way, these lengthening strings, the vertical gap between these two is very small. But as time goes on, each 2-ball snapshot shows a very steep drop-off. That steepness is growing in time. It's speeding up in this direction, but not changing what it does in this direction. But the reason I love this apparatus so much as a teaching tool is all of that remains true even if you change the angle at which you launch the ball. There's so many subtleties here, it's insane. The spacing of the strings is still not different. Incidentally, the spacing of the strings shrunk in the x direction. If you have a launch speed horizontally, you're only putting some of that launch speed in the x direction if you aim your cannon upward. So they get close together, and now we see that arc that all the textbooks and everybody's been telling you happens when you have a projectile near the surface of the Earth. But, like we keep saying, we're doing repeatable science. So let's do a test and see if that quick launch matches our prediction that the laws tell us should happen.
Oh, it hit one of the balls.
It did.
Hold on. It hit this one. I don't know if you
Pesky.
can tell.
You're fired. I'm talking about the ball, not Mary.
This way.
How many clicks do we do? One?
One click.
Let's
But I'll
try
still
this
wild
again.
one.
Yay! But what you saw is, I hope we saw that the ball is matching the path that these pink wiffle ping pong balls are showing us. Slowing down on the way up, speeding up on the way down, but consistent horizontal.
Now with that wonderful setup, time for the quiz. So, there are some physics problems that are so well known they get named. Right? Most of your physics problems like question 2 in chapter 3, whatever. But there are a couple that are so well known, so useful, we give them names, like the Turkish waiter problem, or the neighbor problem, the salesman problem. This is the monkey hunter problem. So, for this setup, I will not answer a school phone call right now. That's how much I care about it. I am a hunter. And I am out hunting monkeys, because apparently a hunter's got to hunt, like whatever. So, I am out in the wild hunting monkeys. And because I am a knowledgeable hunter, I know about my quarry. The monkey is not at all used to technology. So when I fire a gun, there's a very loud noise, there's a very bright light, and that is going to terrify the monkey, right? Because suddenly there's a gun going off. And the monkey's natural reaction to being scared is to go, ah! Which means it's going to completely let go of the tree and start falling. So, to walk through the mechanics of how we have this set up here, I have my gun with a sight on it. And we have our tree here that has an electromagnet. So, if on the barrel of this gun is a switch, and when that switch is closed, when that switch is closed, this electromagnet is on, and it holds the monkey in the air. As a projectile leaves the gun, right? As the projectile leaves the gun and throw this switch, the magnet turns off and the monkey drops. So I know that the monkey will start falling the moment the projectile leaves the barrel of this gun. The question is, where do I need to aim my gun? So the straight line of the gun, where do I need to aim it so that I can hit my target? Why below? Why below?
Because it's gonna fall faster than that one is gonna start.
Right. So because I have to lead my shot, right?
Yeah.
So it's going to be moving, so I have to lead my shot. Those of you who play, shooting games or throw sports balls or whatever, you understand this concept, right? You throw the ball to where the person will be, not at them, right? So we lead our shot. Are there any other guesses about where I would need to aim? What? Bottom of what? So we're just naming parts. Great. Okay. So aim at the thing, because we want to say that we've tried. Great. Any other thoughts about this? All right. Yes? Sure, triangles probably going to be useful. Now, I'm going to give something away here. This is probably something that your teachers may have done at some point. This is one of those tricky questions that you'll see on an exam, where the answer to question 4 is literally in the description of question 3, and it's to figure out if you've been paying attention. So, I'm going to give you a big clue here. If I am firing the gun, we know that the object will fall and the bullet will fall as it is moving through space. Where do I need to aim the gun to hit the monkey? Ryan was literally lecturing you about 3 minutes ago. Yes, the monkey is going to fall. Yes, the bullet is going to fall. Exactly this much. This is literally the exact homework problem that we worked out immediately before we quizzed you about the homework problem. So, this site, there's a slight giveaway that might help this side of the audience as well. Notice there's a target on the magnet that is the same distance above the magnet as the sight of the gun is above the barrel of the gun. So, this is aimed directly at that target, and when I blow, shot the monkey. Now, here's the follow-up question to really see if we're paying attention. How did I know how fast I needed the ball to go to get there? How did I know that I had the correct muzzle velocity to hit the target? How did I know the muzzle velocity of this? Sure. No, that's perfect. Straightforward. I didn't know the muzzle velocity. Because we don't need to know those numbers, right? If we fired a different muzzle velocity, all that would change is the time, right? So if I shoot really hard, it hits the monkey here. If I shoot less hard, it hits the monkey here. But the point is they're still traveling for the same length of time. This is also true under any muzzle velocity, under any amount of gravity. Put this on any planet, it still works. That's why this problem is one of the ones that is so good that it has an actual name, right? It is a widely applicable, so many detailed kinds of problems. And now that you've heard it, at some point it's probably going to show up on an exam. And you're going to be like, yes, I saw that guy shoot a monkey. I know how this works. And that's kind of the whole point of all of this.
So, as Pete mentioned, we've done Newton's first law. Objects in motion tend to stay in motion. Objects at rest tend to stay at rest, unless acted on by an unbalanced force. Second law, you push hard, you get more change of motion, but there's more stuff, you get less change of motion with that push. So let's look at forces a little more closely. And probably the most quoted, least understood part of Newton's laws is for every action there's an equal and opposite reaction. To dig into this, I've got a cart, a piece of mass, and there's a spring-loaded plunger here, and if I push my button, it can pop out. It gives a push. So, again, we start with kind of the trivial case. If I put my car on the track, and I release that spring, it's going to push back on this part. It's fixed. And it scoots across the track until it's stopped by something else, and other forces put on it to stop it. So this thing pushes, and it moves. What's making it move? The spring obviously is doing it. What's pushing back? That thing, I don't know, like the wall.
Yeah, the wall. Let's call it the wall. So if I place my car out here and I apply my force from the car, there was a force. We watched it pop out. We heard the spring release if we're close enough. Nothing happened. Turns out forces are really codependent. They need to go to therapy, I think. They only come in matched pairs. The car is only pushing. They were exactly right. This thing applies a force, but unless there's something there to push off against, it doesn't feel an equal and opposite reaction force that gets it moving. Now, if you're thinking hard, you know, well, you said they only come in matched pairs. If it's just out here in air, there's an air molecule that's now zooming across the room, but we don't see that.
and it wasn't enough mass to get this going. There was an equal and opposite push. Now, I can maybe further convince you if I've got this tool. It's probably been a long time, more than your lifetime, since you've put oranges in a scale of the produce section that did this. It tells you how hard you're pulling on this hook. It's a spring scale, thank you. So I can pull on this, and it tells me how hard it's getting pulled. Pete could hold it and not let it go anywhere, and we know how hard I'm pulling on Pete. But the law I've given you says that's also how hard Pete has to pull on me. Let's see what happens if we both have our own spring scales. I'm pulling. If he doesn't let it go anywhere, he's responding with an equal and opposite reaction force. For every force, there's an equal and opposite reaction. You all feel it on the chair right now. Gravity's pulling you down. Why aren't you falling to the center of the earth? The chair is pushing up on you equally. So, we've spared no expense. We went and bought 2 identical Fisher-Price remote-controlled cars. And we've been talking about Newton's laws and how they work. And you're saying, okay, if I push go on this, one of these cars should go. Why are they identical? Because one remote sends the same signal to both cars, telling them to do the same thing. I can compare what a car on a regular road does versus one on this weird road, a wooden platform that's on these wooden dowels. That light's on. So, why can this thing even go? The tires are gripping the road. The tires are pushing back on the road, just like my shoes are pushing back on the floor. Why do I change my motion forward when I walk? Because my backward push on the floor, it doesn't get the floor moving that way. I end up going this way because the floor is pushing back on me. But clever observers know some of our tricks by now. When something can roll, things get weird.
Ouch.
This one acted as we expect. I say forward on the remote, this goes forward. Did this one go forward? Yeah. Less forward. What did the platform do? It went back. We all saw it. The third law is the reason why. Actually, all the laws is the reason why. That wooden platform was mass at rest. Why did it change its motion to go backward? Because it was forced to go back. So one force of one set of wheels could push back on the wooden platform, but simultaneously push forward on the car. So what you got is both masses moving in opposite directions because they're feeling opposite forces. If we did some math and knew their masses and how much they accelerated, we could show, oh, those forces were exactly equal.
I challenge thee to a race.
A race?
Yes.
Sure, let's do it. So I'm claiming that I only can walk because of this equal and opposite reaction force thing. So let's show them another version of this demo. On your mark, get set, race. I'm not working very hard. I'm listening to Mary's wheels and she's trying her best to keep up with me, yet goes nowhere. What have we done? We've completely removed that reaction force that can propel her forward. On your mark, get set, go. She's running in place because she can't achieve that friction coupling with her shoe in the floor because she doesn't have a shoe. She has a wheel that can roll. Do you want to show them how you actually skate?
Oh, yeah. To actually skate, I always tell people to think about zombies searching for brains. They kind of wobble side to side. So if you push to the side, my wheels can't, like you can see me, I could break my ankle doing this, right? But if I push to the side, my wheels don't slide. So I push sideways and sideways and sideways and sideways.
So another theme of the show is every law we're talking about, you could do a playground version of it preschool. So Mary and Peter are going to play catch. So Pete has some mass, and he's going to put a force on it and push it across to Mary, and she's putting a force on it to stop it, and puts another force on it to send it back. Action, reaction. They're getting pushed back when they receive.
You know it's coming.
But that's really light ball. Let's make this exciting. Can you get a heavier ball?
Sure.
I love you, little man.
Sounds like something's breaking.
Yep, no, we're not.
Oh, just the glass we broke yesterday. I don't get to show it to Bill now.
Ah, medicine ball, 15-pounder. All right, so they're going to play catch with this ball. And yet again, Pete applies a force. Mary has to apply a force to stop it. Smooth. All right, so let's watch Mary closely. When she receives, she has to put a force on it. And when she throws, she has to put a force on it. Each time she does that, both versions, she gets a little faster in her direction backward. To my left, your right.
Oh
So-
God, it gets worse.
Heavier, 20 pounds. So, yeah, usually you're stuck to the earth, and if you want to throw something, you put all your push in, it makes the ball accelerate. But there's a thing called recoil. When Mary throws the 22-pound medicine ball to Pete, we know that something's pushing in that
That wasn't
direction
good.
on her.
My body's in a tense.
We know that something's pushing in that direction on her. Don't care about the ball. You have to see the whole system. Two masses. The reason we can now see it is, yes, because she's on wheels, but because this thing is on par with her mass. If something close, if it's not a beach ball and a person, you get to reveal that equal and opposite push because of a throw. It's technically called an explosion.
So, the first ball. Sorry.
Are you okay, Mary?
Oh my God, I'm so good.
Okay.
I've had a 250-pound person collide with me in skates. I'm okay.
I see.
But, sorry about that. I was trying to sneak out. So the first ball is about 10% of my weight. The second ball is about 15% of my weight, which is why we use it for that second part.
All right. So, we've talked a bit about how technology has helped all of this, right? The only reason that we can figure out things the ancient Greeks couldn't was because we have better technology than them. So, we've talked about walking. We've talked about roller skates. We've talked about horse-drawn carriages. We've talked about cars. That leads us to the next most interesting mode of transportation, sailboats. So, since this is a landlocked room, we have a sailboat here. We have a sailboat, and we have a means of generating wind. So, how does a sailboat work? Yes, wind. Thank you. All right. So, this is going to generate wind, and it's going to push on our sailboat. Now, we already saw when Ryan was doing the cart, and he had the plunger pushing against only the air, not much happened, because it was just the air. But this big fan allows us to have a lot more air, so much more air, that we can actually start to notice its effects. So if I get this fan running, it takes a second because it's building up some speed. Sailboat. So, the fan got all this air moving, and that air hit the sail and started pushing the sailboat back. Right? But we've already established there has to be matching pairs here. So the air was enough to push the sailboat. But the fan originally pushed the air. Wait. So why didn't the fan move? Why did the fan stay still if it was pushing against the air that hard? Yeah. Because engineers were paid a lot of money to make sure fans don't fall over every time you turn them on, right? So this has a big heavy base, it has wheels, it has grips. And those grips are pushing against the earth to hold it in place. This sailboat is big enough that we can explore another question here, right? So the big danger of sailboats, the big thing they're always worried about, is the doldrums, right? What if you were caught out at sea and there is no wind? Now, I'm sure some people have thought, I have a fan, right? If I take my little fan and I just point it at the sail, can I propel us home? Right? So we have the fan now mounted on the sailboat. Do we think this will work? Yeah, danger time on the boat. Do we think this will work to propel the boat? All right. Why not? All right, I can see some murmur. I see a lot of you just are like, if this works, I would have heard about it by now, right? All right, why would you think it would work? All right, so let's find out. I'm going to get this going. It's going to get up to speed again. All right, full speed. We can see the wind going. And it is stationary. Now, just to prove that I am not being a trickster here, we're going to pick up the fan. And then immediately start pushing the sailboat. So we've already established that the fan doesn't fall over because it's pushing backwards on what it's standing on. What was the fan standing on? The boat. So the fan, to keep itself upright, was pushing back on the boat some amount. And then the wind coming off the fan, was pushing on the boat some amount, which happens to be exactly the amount the fan is pushing back. Now, just to show that it was not like the fan's too heavy or something, if we take the sail out of the sailboat and we turn it on again, right? Instead of a sailboat, we now have a swamp boat, right? And the fan is powerful enough to propel the boat across the water. So, we have done walkers, we've done horse-drawn carriages, we've done cars, we've done sailboats. What's the next most interesting means of transportation? Airplanes. There is no complete theory of how flight works. Most of it is somewhere between Bernoulli's principles and a kite, and a little bit of fan boat. Done. What is the next most interesting means of transportation? Rockets. Exactly. So we have to talk about rocket propulsion. Now, as luck would have it, we've already done the rocket demo for you. You've already seen rocket propulsion today. When did we show you rocket propulsion? Yeah. When you're firing the thing? That's a cannon. That's kind of different, right? Because this isn't a form of propulsion. We just pushed it once and then it went on its own. Right? So that's just throwing. But you have seen an honest-to-goodness rocket today. That's right. Mary throwing a medicine ball is rocket propulsion. Right? So the definition of rocket propulsion is throwing stuff in the opposite direction of where you want to go. That's all it is. In the very dry, very technical definition, that was a rocket. There are many kinds of rockets you've heard about, right? That if they have solid fuel, if they have liquid fuel, if they're ion engines, right? All that kind of stuff. The only difference between any of those is what they are throwing behind them. All of them are throw something in the opposite direction you want to move. That's all it is. To show it off a little bit more, because we have to go extra, because you came all the way here, on our boat, we have a CO2 fire extinguisher. So this is a big container of pressurized gas, normally used to put out fires. So we pull the trigger, and it fires everything, and it will release CO2 gas out a nozzle, out this cone. Inside this cone is a nozzle, or more accurately, 4 nozzles. One pointing up, one pointing down, one pointing left, and one pointing right. Why would you want 4 nozzles in a fire extinguisher? Right, it's going to spread it out, but the cone's really doing most of that, right? But it's going out, but the cone is what's aiming it. Why would we want an up and a down and a left and a right?
So the nozzle doesn't move around
Right, why wouldn't the nozzle move around if we had 4?
because of the reaction pairs.
Exactly, because it's in pairs. So the up is going to push it in one direction, and the down is going to push it back. And the left and the right are going to cancel each other as well. So you are going to have all of those forces balancing each other, and it's not going to have a net force pushed against the user. But if, for example, you bought an extra one of these, so the company that refills these doesn't know about it, and you cut off all 4 of those nozzles, so now all of it's only pointed in one direction, and then you put that one direction to be out the back of a boat, you get something that looks an awful lot like this. If your ears are sensitive, you might want to do something about it. Mary, on your count.
1, 2, 3.
Scared the Jesus out of me.
So we've established that forces have to come in pairs, right? We've seen this pair reaction here, but this does leave us with a bit of a limitation, right? If forces always have to come in pairs, then when we try to move things, we are limited by the limits of our human body, right? I cannot exert a force with my hand that exceeds the amount that I can pull my own hand, unless we get clever about things, right? So forces come in pairs, but if we're a little bit more clever, we can manipulate series of pairs to do more interesting things.
Right, so if forces come in pairs, they always cancel. Again, that quote, limited by the frailty of the human, of human ability. Do you think I can lift Pete off the floor, or off this table?
No.
Yes.
I'm going to give it a go. Ready? My feet are off the ground. I got nothing. Right? We had a little weeble wobble, but that was about it. But is there another thing I could do?
Yeah, you can use a lever.
Yeah, check that out. Right? I don't have to exert my whole body at all. We were actually debating this morning if this young man here could do it. But he's like, I'm not trying.
No.
I'm not touching it.
No.
This is actually terrifying. You guys don't realize because we almost knocked this over before. Right? So I'm using less force than I did before. Thank you so much. But what am I compensating for it with? I thought I heard. I was further down the ladder, right? Distance. I gave up force and I used more distance, and it had a multiplying effect on that force. Something that your teachers might call torque, right? But it gave me a mechanical advantage, right? So I had a mechanical advantage because I was able to multiply that force. And for most people, it's pretty surprising, the idea that I might be able to lift Pete. It's less surprising for people. Sorry, I came all the way out of the room. It's less surprising for people to think that feet can lift me. But I am surprisingly difficult to lift. So we're going to take a look at this. Now, why Pete and I do a lot of this? Pete's my work brother. So I trust him literally with my life.
So Mary was able to lift me on the ladder, and we're going to now switch to a different method here, where I'm going to try to lift Mary. So this is a pulley. All right. So Mary is attached to one end. The rope goes up, is around pulling to me. A pulley is a device that only changes direction. So if I pull down on this rope, the other end of the rope goes up, and I'm going to try to lift Mary.
I feel like I'm being weight the last 2 days.
Now, this kind of sort of works. And the big reason it kind of sort of works, instead of really works, is that I am decoupled from everything except Mary, right? So when I pull down on this, right, no matter how hard I pull, if I bring my legs up, really all that changes is the length of rope between us. I'm not using any muscles to pull on her, because as soon as I start to pull, I just lift myself up, and my muscles don't actually matter. If I really wanted to use a bunch of muscles, I would have to strap my feet to the ground, right? This is what happens if you get on like a very competitive bicycle, right? Your feet are latched into it, so you can actually pull on the pedals with your muscles. So in this situation, I really can't use my muscles at all to lift her. All I can do is hold on to the rope and not let it slide. But this is only one pulley. In this situation, we now have 4 pulleys. So now I have one rope. So this is one length of rope going through a number of pulleys. But you can see here that it goes that I am only connected to one rope, one length, and Mary has 4 ropes attached to her seat. So I can now hold Mary up in the air, right? And we can see I'm not actually trying that hard even, right? Like you can see a little bit of tension in my wrist, but not much. Why is it so easy for me to lift her? Right. So we have now done some trading around of forces, right? I am pulling on this rope with some amount of tension, right? Tension is just the word that we use for force when it's along a rope. And I'm pulling on this rope with some tension. But there are 4 ropes pulling on Mary. So there are 4 times as much force pulling up on Mary as I am pulling down on this rope. But I'm not doing this for free. Notice what happens. So if I take about 1 meter of rope, right, and let it out, Mary doesn't drop 1 meter. She drops about 1/4 of a meter. Because when I lengthen this rope by 1 meter, each of those 4 ropes only lengthens by 1/4 of a meter. So I am trading force for distance. Now, some of you who may have seen this before or are going to see more of this, you might hear about a thing that is like the sum of the force times the distance, right? Work. We're not going to get there today, but the point is that both of these have the same amount of force and distance, right? I can directly trade force for distance to lift Mary up this way. Now, this was, kind of cool. I went from not being able to use my muscles at all to being able to hold her up with one hand. What if I wanted to lift Mary over comparable distances with only one finger? Not by like pressing a button, right? But can I exert force with only one finger and get Mary to travel the same distances that we were getting on the block and tackle here? And to do that, we have to switch to a completely different methodology, right? So we're going to be moving away from ropes and pulleys
Big spring.
And moving on to that. So that is the spring from a garage door. I don't know if you've ever tried to repair a garage door or seen someone do it. It's low-key terrifying. That spring is a giant spring, right? And we have Mary now going to hang off.
Careful.
Ha. If my life expectancy abandoned.
So we can see that right now the spring is just sitting there. Right? The spring is just there.
Put the ladder a little bit far away.
And then when as Mary kind of eases herself down onto this. Yeah. Now, go. Right. And as Mary eases herself down, right, we get to some point here where Mary is now kind of just stable, sitting on this spring. So, I am now going to push on Mary with only one finger, right? One finger just pushing on her foot. And I'm getting distances easily comparable to what we got before. As you can see, I'm not working at all, right? I'm exerting no effort into this. And we're getting huge returns. You still have to explain it, folks. So this is now a completely different methodology. In these cases, we were trading forces and distance. In this case, we can see I'm not even moving my hand really. Right? I'm barely tapping her to get this. So I'm not trading force with distance, but we can also see that I'm tapping her repeatedly. So instead of one big pull, I'm tapping many times. Right? Which I think Ryan might be a little bit better at explaining here.
Okay, thanks, Pete. All right, now what Mary's holding is called an accelerometer. It's telling us which way her acceleration is happening, which, if we believe the second law, tells us which way the net force is pointing on her. So you can keep track of when she's being pushed up versus down. Red lights are pushed up, green lights are pushed down. As Pete just got to the doorstep of, his little pushes that could accomplish so much, they have to come at the right time. If Mary is sitting still on her springy swing, that says 0. She's not accelerating. She's not experiencing an unbalanced force, but she is experiencing some forces. Gravity pulls down, but the spring pulls up. What's special about a spring is the more you stretch it, the harder it can pull back on you. So right now, those forces are balanced. But if she's up here, the spring is weaker and gravity is stronger than it, and she accelerates down. When she's at the bottom of the balance, the opposite is true. The spring is now elongated more, it pulls harder against gravity, and it wins out. And this goes back and forth, and if you can cheat the system and get more to happen, if you add forces in the direction of the spring at the right time. So that when she's down below equilibrium, I can add an upward push, and that'll get her moving through equilibrium more and achieve a higher height to come back down, and back and forth, and back and forth. If you try to push on somebody at the wrong time, this is like my kid's at the playground and wants to go home, she's tired of swinging, I push while she's on her way back. If I want to stop Mary, I push at the wrong time, and I work against the push of gravity and take away, word we haven't used today, energy from the system. That'll be in our future lecture. So the fancy word for that is resonance. So this is going to seem like sound is a totally different topic. I've got this tuning fork going, and it's attached to a wooden box with an open end that when it points towards you, you get more of it. Sound has to obey the laws of physics, Newton's laws, because it involves a medium that is massive. If you're vibrating air, that's how sound gets to you. Air doesn't leave this box and travel across the room to your ear. I'm able to change the density of the air in the room by pushing forward on it and pulling back on it. Push forward, pull back, and it creates areas of compression and rarefication that your ears are tuned to pick up as a tone. This one says 440 hertz on it. It's called A in music. And I have a second one that says the same thing. If I ring this one, my ears are pretty bad, but not that bad. That's the same note. So if I can do this experiment, if I can push one fork at the right times, it's going to want to vibrate. If I match it, if I match the pushes and pulls from one fork, it can get the other one vibrating at the same rate. It's in resonance with it. And it works both ways. To recap, I've struck one fork, and it made the sound, made the other one get going. But if it's not constructed exactly the same, and it doesn't have the same mass, if one of these forks has a different inertia, tendency to remain still as the other one, now I can try the same experiment. I put a little rubber band on that tuning fork. Doesn't do it anymore. This one still has a frequency. It'll make a note. Whoops. But it's not the note that this one wants to get, and it'll get it going. They're not in resonance because they have different masses. Mary is going to give our grand finale on that same idea.
Alright. So timing matters. Timing is everything. And I had a question for you with this, but we're going to ask it now. What would have happened if Pete kept on pushing on me and never stopped? What's the goal on the swing set?
To get us right.
Over the bar! Over the bar! I'm going to go over the bar! Right? We would never make it over the bar.
You would have hit the ceiling.
Right? We have limitations to how far we can go. Right, I would touch the ceiling here. If he went further, I would crack my head on that eye bar, and everybody in here would need therapy. Right? And so here instead, we have, my point with this is timing is everything, but there are limitations to what we can do. Right? There are limitations that we can't reach. You should Google at some point the Tacoma Narrows Bridge, right? Teachers write it down, show your students a video later. It's a great example of how timing is everything, and sometimes we can push things to their limits. So here, I have a non-alcoholic beverage glass. And if I send sound waves into it, oh, and I forgot to turn on the camera. Can we get the camera working? And if we take a look, we can see that it's positioned in front of this subwoofer, but it's not touching it, right? So this subwoofer is going to send out sound waves, but it is not going to touch the glass. Now, at this point, we've seen with the tuning fork, sound waves are pushes and pulls, right? The tuning fork vibrates back and forth, it vibrates air molecules, it vibrates the eardrum. So this is going to vibrate that glass. But I'm going to have it going at like 1,000 hertz. Something I need you all to know. This demo is going to have strobing lights with it, and it's also going to have high frequency sounds. If you are sensitive to light or sound or have a seizure condition, you may choose to excuse yourself at any time in the next few minutes. I will not turn it on until you have gotten to a place where you feel comfortable. Right, so we're not going to be able to see this. So that vibration is going to be happening at 1,000 hertz. Our eyes see things well at about, what, 33 1/3 hertz vibrations per second? Something like that. So since we can't see it with our naked eye, I'm going to put a ping pong ball in there. so that we can see that vibrate. We're going to turn down the lights a little bit. Let's take a peek of what that frequency was. Thank you so much for doing these for me, Bill. All right, and we're going to turn this on. And ping pong balls weeble wobbling a little. Oh. Check that out.
Bouncing a lot.
Look at that go. Right? That's pretty good. It's moving pretty quickly, isn't it? I found a frequency where the sound shakes it and it shakes back. Right? Timing is everything. If I turn this a little bit up, it's not gotten any quieter, but the ping pong ball has, just about stopped. Right? Now turn it back down. So that magic frequency that feels really good. Oh, look at that ping pong ball go. Right? All right, so that's it. That's our demo show. Thank you. No, I'm only kidding. What are the limits of that glass? Right? It's not going to break right now because what is the ping pong ball taking away for it? It's taking some of that thing called energy that we haven't defined this whole time. Right? It's protecting the glass. It's taking a hit for the team is what it's doing. So let's try instead. If I do this now, I'm going to turn this up again. This isn't exciting at all, is it? You can't see it vibrating. What if there's a way that we can make it vibrate? Enter the strobe light. I'm going to put it down for the moment and get it tuned. So the strobe light, what it does for us is it makes a really bright flash at 1/10 the rate at which this is vibrating. And so I have to go slowly with it because if I go too quickly with it, the knob is really sensitive. So, all right, so right now, this is almost exactly tuned to match this glass, which you're going to see is not interesting. That doesn't look interesting at all, right? Right. Because this timing happens back and forth twice every cycle, up and down, twice every cycle. If this is going at 1/10, it's actually like the whole cycle is the up and the down. Anyway, if this is going at 1/10, then I'm catching it at even moments. I'm catching it back in its original spot. So I'm going to tune this just a little bit off. And now we're going to get this thing going. And it's going to get loud. Can you see it moving a little bit? I don't know if I see it moving.
More off frequency?
Yeah, I'm going to play around a little bit here. I'm not seeing it go.
You want to change your strobe frequency?
Go what?
Strobe frequency.
Oh, change my strobe frequency. No. Let's try that. I promise it'll break. Right back in a good spot. That is just a smidge off.
Try changing the frequency.
Right.
Can you wobble? No, not the strobe, the actual signal generator frequency. Wobble it a little.
break weird. This is a new box, but these glasses break weird. But when they break, we saved some broken glass. When they break, you can actually see a sine wave
Funny.
break inside them. You can actually see a sine wave there on the edge of the glass. Right? Which your teachers can explain to you later this school year. But so, timing is everything, but you need to know your limits. So at this point today, we've told you nothing changes unless you change it. The harder you force it to change, the faster it'll change. If there are obstacles in your way, change is slow. Right? That's the math thing. When you go to change something, expect pushback. Right? Newton's third law. You have to act in the right direction, right? That was our projectile bit. Timing is absolutely everything. There are things that you can do to maximize your impact and get advantage over a situation. You don't have to be limited by your human frailty. And absolutely know your limits. So I hope this gives you food for thought that your teachers will be able to elaborate on throughout the school year. Thank you guys so much for coming out today.
Thank you.
Oh my God, I forgot one other thing. Thank your teachers. This is so much work for your teachers.